Consider the differential equation dy dx equals 1 minus y. Right away, I can tell this is a type 6 problem because we're given a dy dx question and it's talking about Euler's method, and even in part C it says find particular solution. So this is a type 6 question, but they want to start off by using Euler's method starting at 1 with 2 equal step size to find f of 0. So Euler's method, different approaches, but in our class we're taught to create a table, x, y. The next column in the table is m, which is your slope equation. The next column in the table is delta y, which is slope times delta x. And then the final equation is your first y plus your change in y. So in this situation, our initial condition occurs at 1 comma 0. So 1 comma 0 is our seed for Euler's method. Slope is calculated as 1 minus y, so 1 minus y in this case is 1. Actually, let's write that out. 1 minus 0 equals 1. And then delta y, this is where I have a feeling a few people made a mistake. M times delta x, our delta x value is negative 1/2. Because you're going down 1 to 1/2 to 0. So 1 times negative 1/2 is negative 1/2. Our new y value is going to be 0 plus negative 1/2, which equals negative 1/2. That value carries down as our new y coordinate. Our slope here, 1 minus negative 1/2, is 3/2. 3/2 times our delta x, which is negative 1/2, is negative 3/4. So our new y value is negative 1/2 plus negative 3/4, which equals negative 5/4. And that comes down negative 5/4. So f of 0 is approximated to be negative 5/4 by Euler's method with 2 steps. So the way that they award points is if you did Euler's method with 2 steps, that's going to be 1 point. So I will give you that point even if you accidentally wrote positive 1/2, because you're demonstrating knowledge of what Euler's method is. You made an arithmetic mistake. You, however, probably won't get the final point for arriving at the correct answer of negative 5/4. Moving on to part B, we're asked to find the limit as x goes to 1 of f of x over x cubed minus 1. And frequently, not always, when you're asked to do a limit problem as a part of a free response question, it's probably going to be a L'Hopital's thing. And in fact, if we look at this, f of 1 is 0, and 1 cubed minus 1 is 0. So 0 over 0 indeterminate, which we have to justify by expressing that the top and bottom limits both approach 0. Therefore, indeterminate. So we're going to apply L'Hopital's rule. So we're going to rewrite the limit expression, f prime of x over 3x squared. And f prime of x, as one student so deftly wrote on their test, is dy dx, 3x squared. And they give us dy dx. So when we go back up to the given information and we plug dy dx, we plug x in, our y coordinate when x is 1 is 0. So 1 minus 0 is 1. And then x value is 1, so we get 1/3. So using L'Hopital's rule, you get an answer of 1/3. So again, you have to show that L'Hopital's applies to get that 1 point. You are applying L'Hopital's rule, and then you get 1 point for having the correct answer. All right, for this separable differential equation, we actually are able to separate the variables. So you can write the separation as 1 over 1 minus y dy equals 1 dx. So that is the separation of variables. That 1 minus y travels together. Plus 1 for separation of variables. When we integrate this, the u substitution on this, often overlooked, many students will write this as ln of 1 minus y, but because of the u substitution, there's a negative. Continue. You get 1 point if you found the antiderivative of the left side and the right side correctly, and 1 point for including the constant of integration. Now, if you found the antiderivatives wrong, you're not going to get this 1 point, but if you included the plus c in this step, chances are you would get that 1 point. Given the initial condition f of 1 equals 0, we can plug these values in for x's and y's. So negative ln 1 minus 0 equals 1 plus c. Ln of 1 is 0. So we find that in this case, negative 1 is equal to c. Okay? So you're going to get the plus 1 for accounting for the initial condition, and I do believe they'd give you credit if you plug it into the wrong equation. You're doing the right thing. Now in our class, I oftentimes solve for y first, so I'm going to show that to the side in case that's the approach you took. Now that we have our c value, we can plug that into the original equation and start solving for our particular solution. X plus c would be x minus 1, and if our goal is to solve for the y in this case, we'll divide the negative across. Minus x, then we can exponentiate both sides, e to the 1 minus x, and when we remove the absolute value, we have either the positive version or the negative version of e to the 1 minus x, and given our initial condition, or rather I should say, because we know that y is always less than 1, when we go down here, 1 minus a number less than 1 will always be positive. So the absolute value gives us a positive number, so we're going to take the positive version of the e rather than the negative. If we solve this for e, or for y, we move the e to the 1 minus x to the right-hand side, from the right to the left, and we move the y from the left to the right, and we get our final expression. Now, I also approached it in the way that I run it in class, where I solve for y before considering the initial condition. So this is another approach similar to this one, but is slightly different. And you can see both of them arrived at the same answer. This is the particular solution given the initial condition f of 1 equals 0. And your fifth and final point comes from having the correct solution for a total of 9 points on this FRQ.